colorectal cancers, vulvitis. And we have Dr. Sourav Bhattacharje from University College of Dublin, Ireland, who will share his expertise related with this topic. Thank you very much, Mr. Sourav, for your time and your willingness to share. Even you are not in a good condition, I heard, and we really appreciate and hope you will recover soon. Mr. Sourav will give his lecture for about 40 minutes. And after that, there will be a question and answer session for 20 minutes. And before we start, please allow me to read a brief of Mr. Sourav's curriculum vitae. Dr. Sourav Bhattacharje joined the Medical College and Hospital, Kolkata, India in 1997 and graduated with MBBS, Bachelor of Medicine and Surgery, in 2004, and he continued to master in biomolecular science or cell biology in the Vrije Universiteit Amsterdam in 2006. In the meanwhile, he moved to Edinburgh, United Kingdom, where he worked for almost a year under the supervision of Professor Vicky Stone at the Napier University. Upon finishing his master, he began his PhD in the Wageningen University in 2008, which he successfully defended in 2012 with a very good thesis grade and quite a few research papers. Following that, he worked for a year as a postdoc at the University of Twente, Netherlands. And from March 2014, he joined Professor David Braiden's group in the UCD School of Veterinary Medicine as a postdoc to develop nanoparticle drug delivery platform for oral insulin delivery. And from February 2016, he joined the UCD School of Veterinary Medicine as an assistant professor in veterinary anatomy. So, Mr. Sourav, you are kindly to start your talk now.
Thank you, Eros. Yeah, I'm not in a very good shape, actually. It happened because of the Pfizer vaccine, which I got here. And apparently the vaccine has given me too much of immunity that for last 1 month, I'm not doing great. So anyhow, that's life. And I promised this to Yesi, this talk, much before I got my vaccine. So I thought it will be really bad to cancel this talk. And I want you all anyway. So thanks, Eros, thanks, Yesi, and thanks to all of you for kindly inviting me. I think Eros has already given an introduction of my career. I have been rather an academic nomad. I'm a physician by profession or by graduation, but my PhD was in organic chemistry and in Netherlands. And on those days I met Yesi, so that bondage of friendship still continues. So, and after finishing my PhD, I did 1 year of postdoc in microfluidics, actually. And then I came to Dublin to start with this European project where we wanted to develop nanomedicinal platform for oral delivery of insulin. So, and then another twist came when I was actually hired to teach veterinary anatomy. So being a human medicine or human physician, I now teach anatomy in veterinary students, while I continue to teach anatomy to human medicine students as well. So the spectrum of things that I have been able to do in my academic career is pretty wide. And for whatever reason, I still continue to do so. Now, there are a couple of things. The project that I will be presenting today is based on colon cancer and colon cancer in humans. This project was run in 2019, actually, before this coronavirus appeared. And it was run in a very good scale. And we have some very interesting data. Now, in my research, I'm very interested in biophotonics. That means using photonic tools for diagnosis and management of different diseases. And of course, my research interest is in cancer. So we started this project in 2019 with some very good collaborations although we could not finish it, we are looking for an opportunity to finish it. The moment the virus disappears and we get back to the labs, some of the redundant work will be finished, and we are hoping that this project will be then published in a very high impact factor journal. Now, having said that, I will slowly start the presentation. So I hope you can see it all, right? So this is this is our school, and I hope you can see the pointer as well. So this is our school, and we have very nice campus in UCD. UCD is the largest university in Ireland. It has one of the best campuses in Europe. And someday, if some of you are in Ireland, let me know. Hopefully the virus will be gone by then, and I can take you for a tour of our beautiful campus. It is really one of the best campus in Europe. Now, hold on. Just a moment, hold on, I have to stop share and share it again. I think I have to share this. Yeah, so the background that I would like to say is that the cancer, I mean, this is pretty much obvious that cancer continues to be one of the principal causes of death and human suffering globally. Now, if you look into the fabric of tumor, I mean, what is tumor? And if you look into this, if you follow my pointer, or let me do the pointer as presenter, let me do the laser pointer. So yes, so now you will be able to see the pointer. And if you look into the concept of tumor, so for example, this one, this is a cartoon, and there are other tumors as well. I mean, it's a bulk of tissue which is characterized by unprogrammed growth and uncontrolled growth as well. And there is a lot of research going on in understanding this bulk of tumor, or the tissue fabric of tumor, which we typically call as TME. In short, it's an acronym for tumor microenvironment. That is what is happening inside the tumor, what is happening at a micro scale within the tumor. There has been a lot of research going on. Probably this is not the place to discuss all this. But what we have found is that this tumor microenvironment, that is the tissue fabric within the tumor, is a principal site of interest. And actually it determines tumorigenesis, the growth of the tumor, metastasis, and immunomodulation. I think we all have, it is pretty established now that tumors also invade different tissues and spread by somewhere dodging the body immune system. And it can modulate the body immunity. So tumor microenvironment has become a place for intense research over the last couple of decades, because the concept is, or the hypothesis is, to understand the tumor, we have to understand the microenvironment. And there are a lot of things happening there. I will just touch base with some of them. But the bottom line is that the tumor microenvironment, that is the tissue fabric of the tumor, is extremely important in understanding the tumor and curbing its growth. If you look into the tumor microenvironment, it is acidic. And it is acidic because the tissue of tumor needs a lot of oxygen because of this humongous growth. But the angiogenesis, or the blood supply to the tumor, is not able to provide enough oxygen because the demand is too much. So what happens is the tumor tissue starts doing anaerobic respiration. And as a result, there is a formation of lactic acid, and that lactic acid accumulates within tumor. As a result, the tumor microenvironment is typically acidic. It is heterogeneous because the cells are growing everywhere, I mean, without any control. So it's pretty much heterogeneous. So one part of the tumor is not equivalent to the other sides of the tumor. It is unpredictable, so it is very, very difficult, if not impossible, to actually model the growth of tumor. And as I said earlier, there is a lack of oxygen because of the tremendous demand of oxygen. So a tumor is typically always hypoxic. And because of this hypoxia, there is anaerobic respiration resulting in accumulation of lactic acid and causing this acidity within tumor. Now, how do we understand if their tissue is having tumorous potential? If you typically look into that, the conventional process is to do histopathology. So you typically take a biopsy material and you do histopathology and stain it with hematoxylin and eosin stain. And then the pathologist typically watches or observes it under a microscope. And from the tissue architecture, the pathologist makes a decision if there's a cancer or not. That has been the gold standard in cancer diagnostics. But this process is pretty simple, and it has worked this has been followed for many decades or many years now. But it comes with certain problems or drawbacks. First of all, it lacks, it misses a lot of data. So there's a paucity of data. It depends on the pathologist, and the pathologists are almost always under tremendous work pressure. So they have to screen a large number of samples. And typically there are inter-individual variations. So they are empirical in nature. There is plenty of space for human error. So they're the same slide. If you give to 5 different pathologists, they might come with 5 different diagnostics. So this is pretty human, it's pretty equal to human error, which is one of the things we, of course, want to obviate if we can. Now, one of the ways that we have tried to figure out is autofluorescence. As I said earlier in the previous slide, that this hematoxylin and eosin staining that is very much prone or vulnerable to human error. And also there is a lot of paucity of data. So you lack a lot of information about the tissue because of its simplistic nature. What we have tried to do is, we have tried to do biophotonic tools based on autofluorescence of the tissue. Because autofluorescence or any fluorescence-based technique is highly sensitive, ultra-sensitive, which is far, far more enabling than typical hematoxylin and eosin slide testing. Secondly, if we just go with autofluorescence of a tissue, then we don't need to do any tissue labeling, we don't need to do any manipulation. The process is pretty simple. And finally, because it is autofluorescence, it is far more resistant toward photobleaching, which has been one of the biggest challenges in typical biophotonic tools using fluorophores. But how do we know that the tissues are autofluorescence? Well, there is enough evidence in literature and in other cases. In case of tissues, for example, here I have shown some of the components of tissues, for example, fibroblast, collagen, different collagen tissues, red blood cells, blood vessels, proteoglycans, and smooth muscles. They are all autofluorescent. So they all have typical emission spectrum. And if you excite them at certain wavelength, they all emit light. And they are all fluorescence without any labeling required. In fact, we have seen that red blood cells are exceptionally fluorescent. And one of the reasons of this exceptional fluorescence of red blood cell is the hemoglobin that is inside it. In fact, within hemoglobin, the porphyrin ligands are the most autofluorescent. I mean, they are really, really fluorescent. And I will show that in some of the slides coming over. Similarly, tumor tissues are also highly fluorescent. I'm not going into a lot of details, but most of its component is highly autofluorescent. So you don't need to do anything. Just take a slide, put it under microscope, and excite it at certain wavelengths, and you will see beautiful images. Now, in literature, the autofluorescence has been, autofluorescence of tissues has been reported, but for unknown reasons, it has never been exploited to a lot extent. In our project, we tried to exploit this autofluorescence of tissues, especially in colon cancer tissue, and see if this type of ventures can give us a very good early detection tool for colon cancer. Now we come to colorectal cancer. Colorectal cancer is one of the commonest cancers, actually. It is the third commonest cancer, and it's mostly adenocarcinoma. That's what we find. I have given some biopsy materials, a typical endoscopic view of colon cancer. You can see it here. It spreads quickly due to high vascularity. And because of high vascularity, it is highly autofluorescent. So that's a good news, because it is autofluorescent, we can use all our biophotonic tools, and it's highly ultrasensitive. So we can really detect the cancer at a very early stage. And as we all know, early detection holds the key for management of cancer. So we really want to detect the cancer at an early stage. And autofluorescence can be a very powerful tool, because fluorescence by nature is a very ultrasensitive technique, and it gives us sensitivity which we will never be able to achieve by hematoxylin and eosin staining. It has almost 1.4 million new cases, and almost 0.7 million deaths were recorded in 2012 in colorectal cancer. It is in fact one of the cancers which is noted more in developed countries rather than developing countries. There are certain risk factors, for example, old age, gender. Males are more affected than females. Inflammatory bowel disease, that is ulcerative colitis and Crohn's disease. These are predisposing conditions. Sedentary lifestyle, smoking, obesity, diet, for example, high diet with high content of fat and sugar, they are risk factors. Alcoholism, there are some predisposing conditions like familial adenomatous polyposis or HNPCC, genetic conditions, etc. Symptoms, cachexia, that means losing of weight, anorexia, rectal bleeding, constipation, nausea, etc. These are the symptoms, some cardinal features of colorectal cancer. And colorectal cancer is always detected, and most of the time detected with colonoscopy, that you can see here. And you can see inside the colon. And if there is a cancer, it will typically look like this. So what are the objectives of that project? We acquired human colon cancer tissue samples, and we acquired normal tissues, precancerous lesions, tumor age, because tumor ages have been rather challenging to detect, because that is where typically the tumor ends and the normal tissue begins. So we would really like to know the age of that cancer, and confirmed cases of colon cancer. We had ethical approval, and we got the tissue samples in collaboration with Professor Aurélie Fabre in St. Vincent's Hospital in UCD. The second objective was to methodically examine these samples by microscopic tools based on autofluorescence. And the third objective was to perform data mining on the obtained microscopic data in order to recognize patterns, developing calibration curve, and modeling. Let's move on. So what have we done with materials and methods? We first collected colonic tissue samples under full anonymity, so we did not know about the patients and everything. The patients gave consent for the collection of tissues, and we did it by surgical resection. So this is typically a glass slide, and this is the colon tissue. And for example, this what we have done, this is just a cartoon to show. So this area was more sort of normal tissue, and this was more on cancer tissue. And we typically chose like this, the tissues, because then we can move the objective of the microscope from one to other side and see how the autofluorescence changes along with the tissue architecture as well. because we are typically interested to find that edge where normal tissue ends and cancerous tissue begins. We stained it with a dye called DCM. I will come back in a moment on the DCM dye. And we typically stained it for 2 hours and 10 millimolar concentration. And then we had epifluorescence data analysis and mining. So we collected the colon tissue. First, we did epifluorescence. And then we stained that tissue with DCM dye. And then again did epifluorescence. Why we have stained with DCM, I'll come back in next few slides. And the imagery, then we did the epifluorescence under 4 filters. One was DAPI, we typically call it DAPI. That is the excitation 357 nanometer, emission 445 nanometer. Second, we call GFP. That's excitation 470 nanometer, emission 525 nanometer. Then we called it a rhodamine filter, where the excitation was 560, emission 630 nanometer. And then finally the cytochrome 5, where the excitation was 628 nanometer, emission 692 nanometer. So rather we had 4 filters, and we are typically moving to the right side of the spectrum with these 4 filters. Now, we did this colon tissue epifluorescence, and we found the maximum emission coming over GFP, followed by DAPI, and these 2 were really high, followed by rhodamine and cytochrome 5. Now, second thing is, I would like to give you a little bit information of this DCM dye. So this is the DCM dye. This is the molecular structure of DCM. It has a complicated name, so we are not going there. We typically call it by this acronym called DCM. Now, what happens with DCM dye is, if the dye comes into a polar environment, that is, a lot of charges are there around it, then it shows a rate shift in emission. So this is typical emission of DCM, and it gives a rate shift. I'm not going into detail right now, but all I want you to gather is that if DCM dye comes in under a polar environment, so if you mix it with a material which has a lot of polar charges, then the shift has an emission shift towards the right. Now, it contains both electron receptor and donor moieties. And the cancer tissue, now why we have done it is, cancer tissue is more polar than normal tissues due to expression of charged molecules like phospholipids, sugars, and proteins. If you look into the architecture of cancer tissue, they are way more polar because there is uncontrolled growth of cells. And with uncontrolled growth of cells comes more expression of phospholipids, sugars, and proteins. And these are all exceptionally charged molecules. So our hypothesis is, if we mix or if we put the samples in close relation to DCM, we'll see that the emission of DCM will have a right shift in cancer. And if that is true, it will give us an additional biophotonic tool to actually detect if something is going wrong with the tissue in early advent of cancer. Now, this is normal colon tissue. There is no DCM dye, just plain and simple autofluorescence. This is normal colon tissue. The scales are all given here. It is given in the GFP filter. So 470 and 470 excitation, 525 nanometer emission. So you can see clearly the normal colon tissue. It has beautiful all the cells and the crypts. I mean, this one is even more pretty. You can typically see the crypts and all the mucus cells. And you can, if you just look into these black spots, these are nothing but mucus producing areas, which are of course a lot of air in it. And that is why it is looking black. So the tissue architecture looks pretty normal. And I think you all are familiar with this type of histopathological slides. One of the things I would like to take your attention is, if you look into this typical, you will see these white spots everywhere. And these are, we have checked it with and zoomed in. And these white spots everywhere that you see, these are nothing but vessels full with red blood cells. I have told you repeatedly earlier that the red blood cells are highly fluorescent because of hemoglobin and the porphyrin base in it. These are basically the vessels. When we made the slice of the tissue, these vessels were also chopped at certain places, and they're packed with red blood cells, which actually you see as white spots. If we really zoom in, we can actually show you the red blood cells. So anyhow, colon is a highly vascularized organ. So you can really see a lot of blood vessels and spots and intermingled or related to all these beautiful crypts and goblet cells. That's what you will see. This is normal colon tissue. We have done nothing, no manipulation on it. We have taken the slide, we have taken the tissue, harvested the tissue on the slide, and we have done no labeling. After putting the tissue on the slide, we straightway took it to the autofluorescence microscope. It is 10x magnification. So this was normal colon tissue. Let's see how the cancerous tissue actually looks. Look into the cancerous tissue. I think the previous one and this one, I think I don't need to convince you that there are a lot of changes. And we have many, many more different images, which I of course cannot bring to in this presentation because of time crunch. But the colon cancerous tissue looks absolutely different. In fact, we have seen cancerous tissue is way, way more fluorescent actually than common tissue. And all these slides that we are seeing, all these images were acquired under identical setup. So they are pretty much comparable. And just by naked eye, you can see the emission is more. In fact, we have done calibration and quantification. And typically, we have seen that for cancerous tissue, the emission is way, way more. Not only that, the fabric of the tissue is also different. If you compare this with this, you will find here, for example, this normal architecture is completely gone. It looks absolutely messy. I think you will agree with me. And the tissue has a lot of these bundles. If you look carefully here, and a lot of other places, for example, here and here, there is a lot of haphazard fibrillar texture that we see. And this is nothing more than deposition of aberrant collagen, which is also very fluorescent, by the way. So this entire tissue texture is completely different from what we have seen before. So these are very interesting data, because if such is the change, such drastic is the change from normal to cancerous tissue, it can be a very powerful tool for us to not only model these changes, we can develop mathematical models, of course, and then actually we can put it into a software where we just put the tissue and the software will give us an indication if there is something wrong. One of the major advantages of such digital pathological step is that we can then obviate or we can then avoid any human error. I have told you repeatedly in the past that in hematoxylin and eosin staining, inter-individual error is one of the major drawbacks. But if we can model all this, and we can, by the way, then we can all put it all into a software, and we can just put the cell into, the slide into a microscope, and then let the software actually do it for us. And if the software does it for us, then we can, of course, obviate or avoid inter-individual variations. And we can scan a much bigger scale of area. And of course, softwares can do things which humans in their naked eyes cannot. So these are very interesting initial data. Now, this is normal colon tissue with DCM. Remember, I have told you that DCM dye, the emission emission will be higher when it is under a polar environment. And by polar environment, I also meant cancerous tissue. Now, this is normal colon tissue. We have given DCM. It looks like this, nothing spectacular. But now wait for the cancerous tissue. So this is just a normal tissue. You can see the structures and everything. Now we put it into cancerous tissue. And I'm sure, again, you are convinced with me that there is quite a change when it comes to cancerous tissue. So for example, when we have given DCM, not only the fluorescence has changed also, but you will also be able to find that there are pockets of high fluorescence. And these pockets are where actually more and more phospholipids and other charged molecules are getting expressed. So DCM is this, I mean, there is much more data. I would not like to go there into very lot of detail. But what I'm trying to say is that the DCM, and for example, look at this site, you will clearly see the collagen deposition. And these are expressing a lot of charges. And DCM can actually show you that. Now, these are very exciting data. For example, this one, we have cancerous colon tissue with DCM. And again, you will see a lot of expression of phospholipids. And you can clearly see that. I mean, you don't see that in normal tissue at all. And we have done a little bit of adjustment of the tissue of the acquisition. And you will clearly find a lot of cell borders actually are getting there. This is nothing more than expression of phospholipids. This is another very interesting slide and what we think is happening here. So if you look carefully here, this is the cell membrane and there is a lot of deposition of phospholipids. And you won't see on here. And there is a sort of a tissue fabric or tissue band, which is very fluorescent at all. So what we think we have acquired here, that this is the transitional zone where this side is more into the normal space and it is slowly getting cancerous on this side. So DCM is also a dye, it's sort of a biomarker molecule that is giving us an idea based on polarity of the tissue. And we think it has got a lot of potential if we want to develop mathematical models based on this. There is a rate shift in cancerous tissues, and we have done some typical quantification. So this is normal tissue and cancer tissue. This is without DCM, so just we put it there, and this is with DCM. And if you just see, what we have done is we have put GFP as 100%, and we have expressed all the other filters as percentage of this GFP. And if I just give you that, there is this, if you put a standard line here, you will see that the ratio by ratio, DAPI to GFP has decreased when you put it into DCM. What it does show is there is a rate shift. That means more percentage of emission is coming into the GFP platform or GFP filter. So there's a rate shift from DAPI to GFP, which clearly shows that the cancerous tissues are way, way more polar. And we have to be cautious because this can be a very interesting trend which researchers in biophotonics would love to exploit more. It's a very interesting dye, very cheap, and it can give you understanding of a tissue based on its polarity. I think more and more researchers should be able to use it. I would like to give a summary of findings and conclusions. Number one, I would say that autofluorescence is a very robust tool for histopathological imaging. It is ultra-sensitive, it is highly quantitative, and it can have diverse applications in oncotherapeutics. I have just given some information, but it is the tip of the iceberg. There is way, way more things that we can do, and we are already doing it. As I said, the COVID-19 pandemic has highly affected, unfortunately, some of our plans because we want to do a little bit more and then publish the data. which we could not do because of the pandemic. However, if with situations improving in Europe, we hope we will be back to our laboratories by at least August or September. And I would like to finish all the remaining experiments once we are back. The important thing is the tissue fabric of cancerous colon is not equal to normal colonic tissue. And this is very interesting part, because this is where biophotonic tools will be highly engaging, as we will be able to detect cancerous tissues or cancer at an early stage. I think that is the major advantage of this type of tools. It's not very difficult as well to employ. Many of the universities nowadays have some sort of autofluorescence facility for their researchers. So I think this will be a very, very interesting tool to exploit in future. Secondly, overexpression of charged molecules in cancerous tissues can provide with an optical beacon for identification of cancer. As I said, that with DCM molecule, cancer tissues have overexpression of charged molecules. I mean, because of this haphazard and uncontrolled growth or proliferation of tissue, they express a lot of phospholipids, proteins, sugars. And these are all highly charged hydrophilic molecules. And because of that, they can give us very interesting signals that something is going wrong if there is an advent of cancer. And hypothetically, that is a very interesting or incredibly important signal for or beacon for the researchers to spot cancer at an early stage. And not only for colon cancer, but for most of the cancers actually, early detection is a key for fruitful management. So because of these biophotonic tools, we are able to detect cancers at a very early stage, which because of its ultra sensitivity. So these things need further exploration, and more investigations need to be done, because if it succeeds, we will be moving into the domain of digital pathology, where a lot of human empirical errors can be obviated. In addition to autofluorescence, it provides opportunities for early detection and developing screening modalities. So these biophotonic tools are fast, engaging, and ultra-sensitive. So not only these are there for early detection of cancer, but they can be used for screening modalities. And when I say screening modalities, I also mean that screening of cancer cases in resource poor areas of the world. I mean, nowadays, a lot of these fluorescence gadgets, they are being miniaturized and put into portable handy, or machines or instruments that can be taken to resource poor areas of the world, and we can do a lot of screening, fast screening rather. Again, that moves to a different domain, and I foresee that will be there in next 10 to 15 years, that we will have all these gadgets ready, and it will completely replace the hematoxylin eosin staining tool that we have now. We can do a lot of texture analysis. Now, I have not touched base with texture analysis in this talk because that will make it too long, but we have done some texture analysis of the tissues. So for example, if I go back, you will see in the cancer tissues, the texture, or there is a lot of deposition of collagen fibers. And mathematically, by simple tools like Fiji, we can analyze this. We can extract a lot of numerical readouts from there, and then we can model it. These days, it is highly possible. In fact, it is not very fancy stuff. If you can extract the numerical readouts, a lot of modeling can actually be done by Microsoft Excel. If you know how to use Excel, you will be able to do that. So we can do a lot of texture analysis on the tissues, which is great. DCM can be an interesting and enabling dye. And I think it's a very cheap dye So if you buy a good package, you are done for life. It's that cheap, dirt cheap. And it is a dye-based technique to calibrate and detect. It's very easy to work with. I got it as a gift from one of my professors in chemistry. It's a fantastic dye to work with. You just take that tissue, you put some drops of DCM on it, keep it for 2 to 4 hours, and then wash the tissue in distilled water. You're ready to go and image. Possibilities and modeling of programming, it's a work on progress. I wanted to present it in a conference in 2020, but it was, of course, canceled because of coronavirus. So we are working on it, and we are looking forward to get back to lab in August and September, and hopefully then we can finish it, because it's a very good data that we would like to publish in high impact factor journal. And we have got splendid insights. You can understand all these data with texture analysis and some modeling. They will make a great paper. So we are really, really looking forward to it. I'm also collaborating with a group in Johns Hopkins University in the US. They're also interested in this type of optical tools, especially in colon cancer. So hopefully when this pandemic is over, our collaboration will continue, and in 2022, we'll be able to do some more intriguing and enabling investigations into using biophotonic tools for investigation into colon cancer. I would like to thank a lot of people. One is, of course, Professor Aurélie Fabre. She is a wonderful person. She provided us with all the tissue samples, without which it wouldn't have been possible to do the investigations. Professor Dimitri Schulz, he's always helping me with all the biophotonic tools. We have you can see it here, we have a UCD Conway Institute imaging facility, and he is the director there. So he's a real microscope guy, and he keeps helping me with all the using microscopes on tissue samples. So a lot of this data, what you see here, has been done in collaboration with him. I would like to thank UCD Research for funding. And these are some of the images of Indonesia, which I found on internet. I have never been to Indonesia, but it is in my hit list. I would like to go to Indonesia. Yes, he knows about that. And it's kind of sad that I could not engage with you completely because of sickness today. But I promise whenever I go to Indonesia with all this pandemic is over, I would seriously go to Bogor. I would like to meet all of you. And who knows, I will be able to give you another presentation, this time physically, on the updates and the follow-up to this type of experiments that I have already shown you. And who knows, I will be also able to enjoy some of the very colorful moments from Indonesia. With that, I would like to thank all of you, and I'll stop sharing, and I would like to engage with you with some interesting questions and answers.
Okay, thank you, Sourav, for your very interesting talk, and hopefully that someday in the future you can come to Indonesia and we will provide you sambal. We have a lot of sambal.
I'm looking for an opportunity.
Okay. Okay. Now we are in discussion session, so we are welcoming for all attendees to give some questions or comments. And you see that we have 41 attendees here. So we have also Professor Husin Alatas here, and also for Dr. Tony Sumariada as the head of Department of Physics. So you can ask directly to Sourav by using giving the raise hand, or you can also use the chat facility, and I will read your questions. Okay. Please, if you have something you need to confirm or you need to know more, this is the good opportunity to ask to Sourav directly or indirectly. Okay, so I think while we are waiting, I have some little bit confirmations. You mentioned that you compare to image normal tissue with cancerous tissue. And in some previous slides, you mentioned that the tumor stage is very important. I mean that the normal
which stage?
Tumor. So
tumor
normal
stage, yes.
Tumor and cancers, and you said that tumor is very important stage. Have you ever get the image about the comparison between normal and also the tumor tissue?
I showed you actually.
That is the cancer or this the tumors?
No. I mean, when I use the word tumor, in my presentation, I use the word tumor and cancer interchangeably.
Okay.
Sorry for that. Probably.
Okay.
So when I say tumor, I intentionally meant cancer.
Okay.
So most of it was adenocarcinoma in colon cancer. So I have already showed you the data that how starkly different they are. I mean, it's completely different.
Okay.
I mean, I have a lot of other images as well. I did not want to overburden you.
Okay, thank you. Okay, for the attendee, do you have some questions? Yes. Is there any questions? Let me check from the chat. No question.
Maybe I will ask a question.
Okay. Please, Mr. Tony.
Yeah. Thank you very much, Mr. Sourav Bhattacharje, here for coming to Department of Physics, IPB University. Yeah. It is an honor for us to hear from you directly about the research on colorectal cancer. We have several faculty that working on maybe this kind of not really not much. I mean computational approach about the cancer. Yeah, the mathematical approach for detecting the cancer. So I have a question regarding the mathematical model and simulation that you mentioned before. This is for what is that? Comparing the image, I mean the image processing, or about the biophysical interaction due to the progression of the cancer cell. This kind of simulation that you use.
Well, what we have done so far is mathematical analysis and trying to develop a model based on the images.
Okay.
These images are 2D images, but what we have also done, and I have not shown it here, because it is based on fluorescence, we were also able to develop zeta stacks and develop 3D models of the tissue as well. And that's where it gets really interesting. Because the moment you have a 3D model, and we are right now using Fiji as a simple tool, but fortunately we have access to much more advanced image analysis tools called IMARIS. And what I have shown you is absolutely 2D information. But we have 3D information as well on the tissues. And in 3D, the cancer tissues become really different. And it's very fancy. You can rotate it and you can see the internal texture of the tissues. So our ambition is, of course, to go 3D and do analysis. And there you can do a lot of different stuff. You can measure the length of the collagen fibers. You can measure the texture. You can measure the, I don't know, you can actually extract tons and tons of numerical data. Once you have that numerical data, you can also do a lot of imaging, modeling, computational biology. And that is what we want to do after this very sad pandemic is over. I mean, most of this data was acquired in 2019. And once we wanted to really go for the real thing, this virus appeared from nowhere and made our life a living hell. So everything was stopped. So no, we want to do imaging on 3D data as well. As far as biophysical interaction is concerned, that is something, again, it's a follow-up. We would like to do that. But again, the work then continues, and hopefully this work will continue until end of 2022 as well. That's the ambition, though.
Yeah.
How far we will be able to keep that ambition of biophysical interaction, we have to see.
Actually,
that's the plan.
Yeah, that's nice. Actually, right now, I'm starting working with my student about image processing. Actually, right now, we were analyzing the what is that? The lung, the image of the lung for the COVID and non-COVID patient. So pneumonia, COVID, and tuberculosis, and we compare those images, using the quantum neural network. Maybe we can also convolutional neural network. So are you also doing that thing using that?
I have not done it. I have not done these things on lungs, but I actually am, because I teach anatomy as well.
Yeah, we use X-ray actually.
Yeah, no, we are using it in CT scans of skulls.
Oh, yeah.
Because we are running a couple of projects on evolutionary biology, and we are using on CT scans of skulls. So, and we are using segmentation and other stuff. I don't enjoy programming a lot. I'm sorry to say this, writing scripts and all this. I get bored. I want other people to do the programming for me, and then I will just use it, isn't it?
Yeah, just get the picture and analyze that image.
Exactly, this writing.
Get the insight.
Oh Lord, I'm not a very script writing guy, I want the scripts to be ready, and I will just put the plugin in Fiji and then run it. But and most of the time these plugins are pretty good. It's pretty good, and I mean, so my students are using it, and we are using a lot of segmentation technique, especially on 3D models. But I'm quite understand that this can be used for lungs, where you have all these spots with COVID and non-COVID and tuberculosis. Especially if it is a CT scan or MRI, you can develop 3D models easily, and you can do a lot of analysis on that.
So do you think the computational for the colorectal cancer is more difficult as compared to the lung cancer or COVID, or just the same? What do you think?
Don't know that, but I personally think lungs will be easier.
Okay. Yeah.
One of the reasons that I think it will be easier is if you look into CT scans, it's very easy to convert the image into a binary image. And once you have a binary image, life probably gets easier.
Yeah, you can do anything with that.
In case of colon cancer, and we have seen that in a lot of other tissues as well, it's very difficult to convert into a binary stage.
Okay.
Because you have completely white face, you already see in these images.
Yeah, yes.
You have completely black face, and there are a lot of other colors in between. Now, the moment you ask the software to convert into a binary, it does funny things. A lot of tissues are lost or
false positive, something like that.
Yeah. So once I did a project about renal cancer, and we ultimately got lost into the same thing. So when we asked for converting it to binary, the software was taking a bit of the cancer tumor and a bit of the medulla, and then it got lost. I guess that will not be the case of lungs. Because if you have lungs, and if either you have fibrosed areas or normal areas, fibrosed areas look white, normal areas look black. So if you look into the typical CT MRI scans of lungs, they're already in black and white. So my personal belief is lungs will be easier than any soft tissue. The moment you are dealing with a soft tissue, probably life gets difficult.
Yeah, but if you ask the computational guy, actually using the machine learning, as long as you have a lot of data and you teach the machine to learn, so at the end we can get something
Yes,
good.
you can, but it's a very time-consuming process.
Yeah, it's very time-consuming.
And sometimes when you do projects, the students have rather time-bound things and other things. I mean, those days are gone that when people used to take a research question and they used to investigate for years and years. Nowadays, you have funding constraints. The student has to finish within certain months or certain.
Yes. Yeah.
So within all, and the student has to get some publications as well. So taking all those constraints, those days were like, in old school days, times of Newton.
Yeah, I can understand that.
Used to keep on researching. Those days are probably. I
would have loved to. That's why people need to collaborate. Yeah.
Exactly. When I talk to my students, I give them the example of Friedrich Sanger, who got 2 Nobel Prizes in chemistry. Friedrich Sanger wrote one paper. He got a Nobel Prize. He wrote the second paper after 22 years.
Wow.
He got another Nobel Prize.
Wow.
But 22 years, he was researching on one thing. Today, if I don't publish each year, probably my university will kick me out.
Yeah, will kick you out.
Those days are gone.
That's a problem everywhere.
Exactly. So research changed drastically.
Yeah.
It is much more mechanized now. So I'm sure a machine can be taught to learn. But the amount of time and investment that it requires with all these constraints is not always compatible. That's all I'm saying.
Thank you. Yeah.
We have a question.
Yes. I think we have a question from the chat. There are 2 questions.
Can we differentiate between one cancer to another? Example, breast cancer and colorectal cancer in terms of their polarity. Uli RC physics, answer is, I think it is yes. We should be able to, because the texture-wise, they are different. Now, we also got some breast cancer tissue at that time. The only issue you will face is that breast cancer in humans, they're not very autofluorescent. We have tried breast cancer. We have tried pancreatic cancer as well. Unfortunately, breast cancer, because our breast tissue as such, because it has a lot of fat, probably, and fat is not fluorescent at all, and it has a different texture, tissue texture. We have seen that breast tissue is not fluorescent. I would not say not fluorescent, but the fluorescence is very, very less. But if you are able to get some images, they will be looking different because the tissue is different. You will see a lot of glandular structures, and the texture will be different than colorectal or colon samples as well. So now, as far as polarity is concerned, I don't know because we have not tried it. But my gut feeling is, yes, you will be able to differentiate. That is my gut feeling. I have not done it, but from my experience, I think you will be able to do it. Okay? Any other question?
I think we have Professor Jarwani from the University of Indonesia here. So if Professor Jarwani would like to ask some questions, please, we are kindly to.
Okay, I will ask something. So if you in the future, you want to have this method for screening, yeah? For screening, it means
Sorry?
For screening.
Yes.
Yeah, for screening. But you see, for screening, you have to take biopsy. That means a biopsy procedure. So that means a little bit invasive, yeah. So if you want to have the sample, that means it will be biopsy. So you have to take. That means if you want to have a screening, do you think if cancer, mammy and breast cancer, maybe for the screening just only X-ray or ultrasound, you can do it without not invasive, yeah. But for this method, you have to get the samples from the colon, so that means you have to take the biopsy. Is it possible for screening then?
Thanks for your question. What I have said is that it can be used for screening techniques in resource poor areas. And let me explain why. I have not talked about biopsy. So you need the biopsy samples. But what I'm trying to say is that once you have the biopsy samples, all you need will be a simple epifluorescence microscopes. You don't need a fancy microscope. You just need one filter, and you just need probably one simple desktop where the software will be installed. In fact, I know in Ireland some people are already programming for that software. The software interface will be very simple. There will be a running play button, and once you click it, the software will automatically do everything for you. And it's not a very CPU consuming software. So what I'm trying to say is once you have the biopsy samples, and you have put it on the slides, of course, the rest will be very easy. And I know my colleagues, some of my colleagues are already doing that. And once you have that sort, and in fact, these microscopes are also getting miniaturized. So those days are gone that you have very huge, heavy microscopes. So they're much more portable stuff are coming. So, and all you need is one filter, which is not very expensive at all. If you have, in fact, if you have just one LED filter, those bulbs keep on running for thousands of hours. And then you have the data. Now, when I am talking of a screening tool, what I'm trying to say is that the software will be able to give you some warning signals. And what we are presuming here is that we will use a traffic signal method. That means there will be 4 colors. Green means the tissue is all right, or nothing to be scared of at this stage. Then there will be amber, which means or something on the borderline. And then finally, there will be a red line or red, which means there is something very worrying. So we are typically trying to use a traffic signal method. So you run the software and it will typically give you a traffic signal system. By screening, I mean that I have never said that it will replace biopsy or anything. You will still need the biopsy. You still need to make the slides. After that, I'm talking of the biophotonic part. When you are using the microscopic tools, that can be accelerated to a lot extent. And that is what I have said as screening tool. Yeah. Not only that, my colleagues here, I know they are wonderful people. They are trying to develop things. So for example, it will be a simple microscope, but you can load maybe 10, 20 slides as well. So it will automatically keep on running. So 1 done, 2nd done, 3rd done. So what I'm trying to say is they're also trying to make it a high throughput screening technique. So you can upload maybe 20 slides and go for a coffee. And once you come back, it gives you all the data in a very user-friendly interface. It will not give you an amazing amount of data, but it will give you a sort of an initial indication whether you need to be wary of a sample. That's what I have meant by screening, not more than that. So you still need to have a slides.
Yeah.
That cannot be obviated. But once you have the slides, you don't need to stain it. There is no need to stain. So that saves time already. Because when you need to stain, for any of these stains, you need to do a lot of tissue manipulation. You have to stain it. You have to then wash it with a lot of organic solvents. And then the more you keep on handling the tissues, you are changing its initial native architecture. Here, you have the tissue, you put it on the microscope, you go for a coffee, come back, it's ready. It will not be exactly perfect. Let's say it will be semi-perfect. That's what I have meant.
Yeah.
Is that okay?
Thank you.
Thank you.
Maybe my what do you call it? I have opinion that screening for person who want to be tested. Is there any possibility that I will have colorectal cancer then? So like that. So that means you have the samples already. So screening the samples. Yeah. Okay.
Yes.
Thank you.
High throughput screening. That's the ambition.
Yeah.
That is the ambition.
Yeah.
Okay.
Okay. Thank you.
No problem. My pleasure.
Thank you, Professor Jarwani. And Sourav, it seems that we are running out of time, but we still have one question we have not answered yet. This is from Sitiani. Very interesting presentation, Dr. Sourav. I want to ask one question. Can you identify the cancer stadium based on the image obtained?
Sorry, you have to go a bit slower. Can we?
Can you identify the cancer stadium based on the image obtained?
Cancer stage?
Yes, stage.
Very good question. That's again the ambition. Now, the challenge here is, and this is a very fantastic question, can we determine the stage 1, 2A, 3B, isn't it? Now, we can, but then we have to instruct the software. Now, there comes the fallacy. When you put the software and you ask the software that this is the image and you analyze it, you have to give it a mathematical threshold that up to this, say, up to 30% A, stage 1, up to 60% stage 2. The issue is, who determines what is the threshold? That is where the challenge we will face eventually. So for example, so we put a sample, and then the sample, we typically extract some numerical readout. And from that numerical readout, we ask the software to grade it at different stage. But the issue is, how shall we determine the threshold? If I say up to 30% is stage 1, then a lot of things will be stage 1. Then we say up to 60% stage 2, maybe 60 to 90% stage 3, and above 90% stage 4. The problem is there is no universal scale, and it completely depends on us. I can say, no, not 30%, up to 40% is stage 1. In that case, more cases will be graded as stage 1 by the software. So to answer your question, it's yes. But the challenge is to put that threshold. It will not be an universal threshold up to what stage 1, up to what stage 2. Because these cancers typically, their physicochemical characteristics vary with a lot of different issues. It varies with age, it varies with ethnicity sometimes, it varies with gender, it varies with physical conditions. So what is the stage threshold that up to this grade 1, up to after that grade 2, that will be something of a challenge. Other than that, yes, staging is possible, very, very much possible.
Okay. Thank you for the answers. And I think we reached the end of this discussion, because I know that you are not in the good condition, so we will not to make it longer than it's supposed to be. And
Yeah.
before we end this,
You crossed good amount of time actually.
yes, sorry.
I was not expecting it.
You have so many powers to this. Okay, before we end these sessions, we would like to give a token of appreciation, a certificate, not a symbol, or of course. and and for this, this is the I think you can see this is the certificate of appreciations, and also we have a closing remark. And for this closing remark, we would like to invite the head of Biophysics divisions, Dr. Ahiruddin Madhu. I think we have Dr. Ahiruddin Madhu. Let's see. No. Okay, it seems that there is some problem with the connection or something. So oh, okay, Dr. Ahiruddin. Okay, could you please to give some closing remark for Dr. Sourav Bhattacharje? I think you are still mute. We cannot hear your voice, Dr. Ahiruddin.
Okay, thank you.
Okay.
Good afternoon, Dr. Sourav.
Pleasure.
Let me introduce myself. I am Ahiruddin Madhu, head of Division of Biophysics, Department of Physics, IPB University. I think the material or the topic you have presented is very interesting related to identification of cancer by optical methods. This topic is still new to us, but very interesting and can be an inspiration for us to be developed in the Department of Physics, especially in Biophysics division. As one of topics of biophotonics in Biophysics division, I hope this activity can continue to strengthen the collaboration that is being initiated today. Of course, we hope Dr. Sourav can come to Bogor someday. On behalf of the Department of Physics, IPB University, especially Biophysics Division, would like to thank Dr. Sourav for knowledge and experience that has been given to us. And see you another event in Bogor, of course. Thank you and best wishes to all of us. Thank you.
Okay. My pleasure. Okay. I will someday go to Bogor, of course. It is my agenda.
Yes.
Now I know all of you. I think there is a lot of. I love the gardens of Bogor.
Mm.
I have seen that, so I'm really very looking forward to go to Southeast Asia. Hopefully, whenever it happens, I will catch my next flight.
Yeah, so you should come to Bali too.
Yes, of course, Indonesia is in my one of the countries that I wish to go, with a lot of historical importance attached to Indonesia. So very much looking forward to it.
Yes, thank you. Thank you for Dr. Sourav for your wonderful talk, and also thank you for the audience for attending and giving attention during this webinar. Hopefully we have some insight from this lecture, and also we really hope that Dr. Sourav, you can speed the recovery and you can continue your adventure in the next future days.
Yes.
Okay, so this is the end of our lecture today. So we hope that we can meet again in the next IPB Physics talk, and with the different theme, with the different research topic. And with this, I would like to thanks everyone for the very nice attention, also question also, and another thing. So okay, with this, the end of this seminar, I will thank you very much for all your attention. Thank you very much.
Thank
Okay.
you. Bye.
Thank you. Thank you,
Bye.
Sourav.
Bye. 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 Pleasure. Bye.
Thank you very much, Sourav.
Bye. Bye.
Yeah,
No.
for sharing your knowledge. And
Bye.
good luck with your second shot tomorrow. Yeah.
Bye. Bye. Bye.
Bye, Sourav.